Welcome to 9.3 part 2. We did the equations with the absolute value. Now we're going to do the inequalities with the absolute value. So once again, we always want to solve for the absolute value or isolate it, whether it be an equation or an inequality, before we do the positive and negative case. Now, first thing we want to do is a couple things. Like, generally what I'll do is I'll identify is this an and or an or. And because the absolute value is less than the number, this is an and problem. So after I establish that it's an and problem, I kind of draw a little number line over here. It's going to do some graphing, and I consider the two cases. Now, the positive case is when we leave this alone. We have 2x minus 5 is less than or equal to 10. The negative case is where we have our 2x minus 5 is greater than or equal to, so we flip the sign, and we have negative 10. So we solve these individually. Add 5. Add 5. So we get 2x is less than or equal to 15. Divide by 2. And we get x is less than or equal to 15 halves. Okay, so I'll put a little mark at 15 halves. X is less than that, so we're going to shade that way. Now we're going to solve this. So add 5 to both sides of this. We get cancellation here, so we get 2x is greater than or equal to negative 5. Divide by 2, and we get x is greater than or equal to negative 5 halves. So that right there, point of interest, negative 5 halves. Greater than that, so we're up here. So there's a couple different ways we could talk about this. We could use the interval notation, that is, this is the interval from negative 5 halves to 15 halves. Or we can say negative 5 halves is less than or equal to x, which is less than or equal to 15 halves, because anytime we have an and, we can always write that as a compound inequality. Okay? So that's that one. So when we move to this next one, the first thing that we need to do before we consider the positive and negative case is we want to isolate this absolute value. So I'm going to subtract 9 from both sides. So here we get our 9, that's gone. So we have absolute value of m plus 5. When we subtract our 9, we get cancellation here. When we subtract our 9 from that side, we have 7, and we still have less than or equal to. Sorry about that. So now we have our positive case, where we leave it alone. We have m plus 5 is less than or equal to 7. And we have our negative case, where we have m plus 5 is greater than or equal to negative 7. So we've flipped the sign, we've done the side, and because we have a less than or equal to, this is an and problem as well. So we want to identify that as an and problem. So solving this, subtract 5, m is less than or equal to 2, and here subtract 5, m is greater than or equal to negative 12. So these are the two pieces we're looking at. Now when we graph this, m is less than or equal to 2, so solid dot at 2, less than or equal to, we're shading to the left. M is greater than or equal to negative 12, so we have negative 12. Shading to the right. The overlap part, because this is an and, so the solution, we could say it's negative 12 to 2, including both those endpoints. Or we can turn this into that compound inequality. Negative 12 is less than or equal to x, which is less than or equal to 2. And once again, we can do that because this is an and problem, and and problems we can always write as compound inequalities. Okay? So, let's take a look at this next one. Next one here, the absolute value is already isolated, but now we have the absolute value is greater than some number, right? So this is going to classically be an or problem. So I write or up there to remind myself that's what I'm doing. Solve my positive case. 4 minus 3y is greater than 8. In the negative case, we have 4 minus 3y is less than negative 8. So we've flipped the sign and made the number negative. So here we subtract 4. So negative 3y is greater than 4. Divide by negative 3. Now we're dividing by negative 3, so we want to flip the direction of the sign like we normally would in inequality. The 3's cancel, and we have negative 4/3. So y is less than negative 4/3. Put a circle, negative 4/3. Less than that, we're over here. Okay, solving this one, subtract 4. And those cancel, we get negative 3y is less than negative 12. Divide by negative 3. Now once again, we want to flip the direction of the sign. That gives us y is greater than, flipping the sign, 4. So put a circle at 4. Shade off to that. So, this right here would be a perfectly valid, like, if we put a little or there, a perfectly valid set notation type answer. If we want to do interval notation, this is two distinct intervals. This interval down here is negative infinity to negative 4/3, parenthesis, because we don't want to include that, union, and we're reading from left to right again, we start back at 4, not including 4, to infinity. So that's how that one works. Okay, now looking at this next one, once again we want to isolate the absolute value before we do anything, so I'm going to subtract 9 from both sides. And when I do that, we have 7 is less than or equal to 2x minus 3. Okay, now once again, we have we have the bitey piece biting into the absolute value here, so essentially, we could rewrite this to look more like this one right here, but this is an OR problem. So this right here, I'm going to write OR to remind myself this is an OR problem. Then I'm going to break it into my two cases. That is, I have my positive case, 7 is less than or equal to 2x minus 3, and then I have my negative case, once again negative 7, so we make the 7 negative, flip the sign, greater than or equal to 2x minus 3, subtract, so add 3 to both sides. So when we do that, here we get 10 is less than or equal to 2x, cancellation here, divide by 2, and we get 5 is less than or equal to x. So this is part of our solution. Or, add 3, negative 4 is greater than or equal to 2x, divide by 2, negative 2 is greater than or equal to x. So, x is greater than or equal to 5, and x is less than or equal to negative 2. That would be a perfectly valid set notation type thing. We could graph these now. X is greater than or equal to 5, dot there at 5, greater than, so we shading to the right. X is less than or equal to negative 2, negative 2, shading to the left. Two distinct intervals, so we can denote this in interval notation as the interval from negative infinity to negative 2, including it, so square and bracket, union, the interval from 5 to infinity. So that's the interval notation. So the last one we have right here, I'm going to go down here to do this. Alright, so we want to isolate the absolute value, so I'm going to divide both sides by 5. Okay, because we want to do that. So 5 cancels here. And the absolute value of x plus 4 is less than 7. Now, we have the absolute value less than a quantity, so this is going to be an AND problem. Okay, so an AND problem. So positive case, x plus 4 is less than 7, and negative case, x plus 4 is greater than negative 7. Solving this, subtract 4 from both sides, we get x is less than 3, and solving this, subtract 4 from both sides, x is greater than negative 11. So we can really kind of put this together here, and you can kind of see it. We're going to get negative 11 is less than x, that's this piece, but x is less than 3, so that's going to be kind of the set notation of that. And we can notice that as well as we graph this. If we graph x is less than 3, circle at 3, shading to the left. X is greater than negative 11, circle at negative 11, shading to the right. This is the part we're looking for. So this would give us that this set piece, the interval. If we want to put this in interval notation, reading from left to right, this is the interval that starts at negative 11 and runs to 3. And that's what we're looking for. So a lot of steps here, but just take it slowly and make sure that you're analyzing whether it's an AND or an OR problem, and always remember to do the two cases, the positive and negative. Negative, always flip the sign. All right, see you next time.